So my name is Daniel Egger. I'm based in Zurich, working for IBM Quantum with Elena. And today we'll be going over some of the tools that we have in optimization. So let's get into it. Stefan has already presented a very similar slide with very similar papers. It's very exciting to see nowadays that because we have the hardware at such a scale that people are starting to test out various algorithms on the hardware, right? And what I want to do now, what we want to do, is to go through a little bit some of the software and tools that make part of this possible. The approach that we will take follows a little bit our journey through the quantum stack. So at the very top level, we have the problem modeling stage, right? How do you go from a description of the problem, maybe in plain language, down to something that a quantum computer can actually start to understand and reason with. Then we have the circuit creation step, right? Building a circuit. And a lot of this you'll see kind of focuses a bit around the QAOA, right? And so there we also need to find parameters for the circuit, and we'll show different ways through which one can actually do that. There are some steps in circuit optimization to get the best out of the hardware, right? Maybe making sure that we don't have circuits that are too deep. There'll be quite a few examples on that. And then we'll also cover some of the tools of post-processing and execution on the hardware. So here is a very broad overview of all of the tools that we will be covering. There's little code bars associated to each of them pointing to GitHub repositories in a lot of cases. These QR codes, they will repeat throughout the presentation. So if you don't manage to snag it now, you can get it later on as well. So I want to start off with the problem modeling. And we have released in the past week the Qiskit optimization mapper, which is on open source. You can install it with PyPI. And it's essentially a package that allows you to go from the description of your problem to Ising Hamiltonians that you can then use further down the stack. So think of this in the following way, right? A lot of business problems, optimization problems, can be formulated in a fairly simple, plain language, right? Let's take a look at the sentence here, right? Find the largest set of nodes in a given graph G such that no two nodes are adjacent. This is, in fact, a plain text description of maximum independent set, right? And you can go ahead and write down what this actually means in terms of equations, and you end up with the formulation down here, right? Now, when you look at this, you can start to ask yourself the question, well, how do I actually bring this into a quantum computer? And this is what the optimization mapper is about. So in this package, we essentially have 4 different things, right? We have the variables, which are our decision variables, and here we support 4 different types. You have continuous variables, which can take on any, let's say, value in R. You have integer variables, something that could take on a value like 0, 1, 2, 3, 4. You have binaries, which take on the value 0 and 1. And then you have also spin variables that the package supports, right? And these are decision variables that can take on values of -1 or 1. And then this is already relating fairly closely to what you would have on a quantum computer, right? Now, to model the problem, we support also all sorts of various terms in the mathematical formulation of the problem. So we have constant terms, right? 3 is a constant, and there you go. Linear terms, so linear in the decision variables, like 3 times x2. Or quadratic terms, so 3 times x0 times x2, that's a quadratic term. Now, often a lot of the classical solvers, they work with either linear or quadratic terms. But it turns out that in quantum, we can also very natively represent on the hardware higher order terms, right? Which is why we also include these type of terms in this package. So having decision variables and terms to sort of make them interact is nice, but you also need to start taking into account objectives and constraints. And so the package allows you natively to build things like equality constraints or also inequality constraints, as we saw on the last slide. So all of this allows you to set up a model of the problem, and then you need to take this and convert it maybe into, let's say, a different formulation, taking, for instance, your inequality constraints into equality constraints with slack variables, for instance, and then ultimately take the result of all of these conversions and translate it into a language native to quantum computing, right? Which are these translators, which will give you things like an Ising Hamiltonian. So here is, for instance, a very, very simple few steps of the workflow. You model the optimization problem with your decision variables. Some of the variables that don't natively fit onto the hardware you would convert, right? For instance, take integer variables. You might convert them to binary, something with 2 levels that you can very nicely represent in the state of a qubit. And also, you need to do things like take, for instance, your inequality constraints, convert them into equality ones with slack variables, and then add these as penalty terms to your objective, right? And this is something that will result in either a kubo or a hubo. And then you can take that and convert it to an Ising Hamiltonian, whose ground state is actually the solution of the optimization problem that we want to find, right? So these are basically some of the capabilities that we have in here. And I think with this, I hand over to Elena.
Sure. So I'm here mostly to walk you through some code examples, but I also sneaked in a little history lesson for those who might be interested. And it's regarding optimization, library, packages, etc. And it's this Qiskit optimization mapper add-on is not our first try of having Qiskit an optimization library with Qiskit. In fact, if you have stayed with us for long enough, you may remember Qiskit optimization. This was one of the application modules, and it did contain some of these key modeling tools that we're going to present later. However, the package had a different focus. It was not necessarily built for these quantum advantage-focused workflows, and it had a few other things that didn't really match into what we are looking for in the future. So we decided to do a bit of a rehaul and just come up with this new package. If you were still using Qiskit optimization, here's your opportunity to migrate. There are actually migration guides in the mapper package. If you have any questions, you can ask me. It should be quite easy to migrate. If you didn't use Qiskit optimization, then I can quickly show you how to use the mapper from scratch. And we are going to use this workflow that Daniel just briefly presented, and we're just going to go through every step and see how you can do this with the add-on. So the first step is the modeling. As Daniel mentioned, we have 4 main ways we can model our optimization problem. A lot of these tools are modular and mix and match, so this is not like a fixed way of doing things, but there's just a couple of examples. So the first way you can do things is with direct modeling. This means you essentially build your optimization problem step by step. So you start by defining the object, you continue adding whatever variables you need. As you can see, we support different types of variables. Then you define your your objective function with different kinds of constraints. One of the, I think, more exciting additions on this package is the inclusion of higher order constraints. You can see over here that we have both 3rd and 4th order constraints, and this is really like a flexible representation format when you can extend to whatever order you would like to, if you consider that to be relevant. Once you have your objective function, in this case a minimization function, you can also add different kinds of constraints. Of course, you have your linear constraints for the linear terms, but you also have quadratic constraints, higher order constraints. Obviously, the larger the order, the more lines it takes in the slide. But you get the gist, right? And there's a chance that you say, OK, cool, this is very interesting to get started into understanding how these constraints work, how the model looks like. But what if I don't want to do this direct modeling all the time? Then you have other options. One option is using DOCplex. This is a well-known library, and we offer converters. So you can just define your model using DOCplex, and you can easily translate it to the optimization problem class. Maybe as a little, I cannot find the word, but a little thing that I want to say is that these do not support higher order constraints. This is something we incorporated into the optimization problem directly. But for most problems, you can probably do it this way. If you want to load from an LP file, you can also do this through DOCplex. Again, this has the constraint that it doesn't support higher order terms, but it's very easy. You can just use the DOCplex model reader, and then you can, again, translate to the optimization problem. finally, you can use one of our pre-packaged application classes. These are very common problems that you have heard throughout Stefan and Daniel's presentations, the traveling salesman problem, max cut, et cetera, maximum independent set, just like this example over here. One neat addition we also have in the new add-on is that we support RustWorkX. So you can define your RustWorkX graph. You can plug it into your application class, and then you can easily translate to the optimization problem following a very similar syntax as you did before. Now, that covers the first step of the workflow. You can see there are different alternatives. Now, for steps 2, 3, and 4, you see that there are different kinds of conversions between variables and penalty terms, as well as constraints. And I just grouped them all together because we do these through another pillar of our add-on called the converters. So this is a little table that summarizes the converters we have. We can convert between variables. We can convert between constraints, as well as constraints to penalty terms. We can convert between objective functions. And we finally have some handy end-to-end converters that essentially gives you a QAOA or HUBO representation of your problem. Now, to oh my God, sorry, it's after lunch, I'm tired. To show how these end-to-end converters can be actually really handy. Here's an example of a step-by-step QAOA conversion. This is actually, there are more steps than you would actually need for this problem, but I put them all just to show you. In this case, we have an optimization problem with integer binary variables, a maximization objective function, and then a linear constraint. Now, you can see that we need to perform up to 6 steps of different conversions to reach our final QAOA formulation. However, logically, if you just use the optimization problem to QAOA, you can get a QAOA in 1 step. And so this is something that adds this convenience without really stopping you from the flexibility of using the converters individually if you want to. The final step of the workflow is translating to an Ising Hamiltonian. I added an example here with HUBO just to also show you the flow of the QAOA converter and the HUBO converter is very similar. In this case, we have an optimization problem. We add integer binary variables, a minimization objective function with linear, quadratic, and higher order terms, as well as higher order constraints. We convert this to HUBO. On line 22, we get our HUBO formulation, and then by simply calling this toIsing function, we can get our Ising Hamiltonian. This is a sparse Pauli object. This is a Qiskit class. And this is what we will refer to from now on as the cost operator of our problem that we can then plug, for example, into a QAOA workflow. So this is almost everything, but I wanted to add an extra step. This is not part of the generic workflow, but is interesting, and it also explains why we have a module in the add-on that's called solvers. And it's because we have a bunch of classical solvers. We have Cplex, we have QAOA, and we also have a SciPy open source solver. The idea here is that solvers are not only useful for checking that our final solutions are good, but they can also help us verify our model. We have an example here where we define a maximum independent set problem instance. You can see that then on line 10, we define a penalty to convert a linear inequality constraint into a penalty. Now, this is a parameter that we can tune. And this means that we could potentially tune it incorrectly. In this example, we see how by validating with the Cplex solver, we conclude that the penalty term that we chose was too small. And the solution that we get with the classical solver is actually not feasible. It's not a feasible solution for the problem. This is a really cool feature of the add-on, and is that it is self-contained in the sense that it allows you to interpret the solutions for that specific application class, right? And this is saving you quite a few steps. Now, if we change the penalty term and we increase it, then we can see that we do get feasible solutions. So yeah, this is just a really quick example of how classical solvers can be really helpful for modeling. And with that, I think we can already go to the next step.
Awesome. Thank you very much. So what I'll do now is to show a little bit some of the options that we have in the circuit creation. Right? So a lot of the tools that we use here are simply standard Qiskit functionality. So there we go. There's many different approaches to actually tackle combinatorial optimization here. And it depends a little bit on the setting and what you're doing, and what I want to do is to give you a few examples of the way that the circuits might actually look like. So the one that everybody typically starts off with learning is the standard QAOA, right? So what you do is you start off from an initial state, which is an equal superposition of all candidate solutions, and that is simply constructed by applying Hadamard gates to all qubits. And then after, what happens is that we alternate the cost operator and the mixer, right? And this is what you can see here. So the cost operator is nothing more than the time-evolved exponential of the Ising Hamiltonian that we obtained from the Qiskit optimization mapper. And the mixer that follows afterwards is nothing more than the time evolved of a Hamiltonian whose ground state happens to be the initial state that you can see here. And then we alternate this p times, right? So this is a lot like a trotterized version of annealing with the additional freedom that we can select the time steps, so the parameters gamma k and beta k, as we actually like to drive us faster towards the ground state. So this is the standard QAOA, but then over the years, a lot of literature has appeared on different variants of QAOA. So for instance, in the warm start, what we do is we solve a relaxed version of the problem. So for instance, if I'm dealing with a binary optimization problem, a relaxed version could, for instance, correspond to taking these binary variables and relaxing them to continuous ones and solving the problem that comes out of that, right? And so this initial solution from the relaxation gives me a warm start. And this will make me change the initial state. So you can see here in the middle column that we have replaced our Hadamard gates with rotations around the y-axis, where the degree of the rotation is informed by the warm start. And now, of course, if you want to preserve the idea or the essence of QAOA in some sense, you need to have a mixer that corresponds to your initial state so that the ground state of the mixer is also the initial state. And as you can see in the circuit, you leave the cost operator alone. You don't need to touch that, right? And so this actually gives you the circuit for warm start QAOA. And then, as mentioned by Stefan, we looked recently into some multi-objective optimization. And there what we actually do is we take the standard QAOA, but we have a cost operator Hamiltonian that is now a superposition of each Hamiltonian of the different objectives, right? So you can see here now that we are building this weighted sum of the different cost operators, and then these get exponentiated, right? So it's a way of bringing the structure of all of our different objectives into the quantum circuit. So I think here I hand over to Elena again, who will show you a little bit some examples on how to build these circuits.
Yes, that's what I'm going to do if I don't get super stuck. Let's see. We're going to start real simple. If you've been, again, around for a long time, you must have seen this a gazillion times. This is the QAOA ansatz in the Qiskit circuit library. It is also a fairly small ansatz because I wanted you to be able to see the gates. I've been having some struggles making this presentation because the moment you go to utility scale, you just end up having these kind of blocks, and it's really difficult to point out what is going on when you have these giant circuits. So some of these examples are going to be small, but it's just going to be for visibility purposes. Anyway, we have our QAOA ansatz circuit that is built from the cost operator we got before. This would be a sparse Pauli op that you could get from the add-on, or you could write it yourself if you really want to. A cool extension of this QAOA ansatz can be found in the QOpt best practices repo. This is, I guess, the third repo, if we count Qiskit, that we are going to be touching today. This is, as the name indicates, an annotated version of the QAOA ansatz. In particular, you can find boxes that enclose both the initial state, in this case, this is a two-layer QAOA, so you can see you have two cost layer repetitions as well as two mixers. Having these boxes allows us to assign certain information to the box. This is actually one of the founding principles is also using Samplomatic, but this has nothing to do with Samplomatic. Please don't confuse it. These are just boxes. The annotations include what kind of layer is there. Is it an initial state? Is it a cost layer? Is it a mixer? As well as the layer number. Now with this, we can do some cool translation tricks that I will show you later. But this essentially looks like the ansatz before, it's just a little bit more orderly. We can do even nicer things. For example, the warm start QAOA ansatz that Daniel introduced before. Here we play around with our initial state and our mixer. We can see that in the initial state, we're adding RY gates. The thetas that I'm using are fake. Don't try to reproduce this. It will not really lead to a good result. To provide a custom initial state, you need to build a quantum circuit with it. However, to provide a custom mixer, you need to provide the Hamiltonian. This is, again, another sparse polyop. The code was a little bit too long to put on a slide, so I just abstracted this away into a function, but you would essentially build the sparse polyop following some of the techniques we've used before. You plug all of these into either the standard QAOA ansatz or the annotated one, and you would get something like this. It is very similar to what we saw before, but you see that both the initial state, instead of being an equal superposition, now has RY gates, and then the mixers have other gate combinations as well. There are no examples for the multi-objective optimization ansatz. This is partially because there's going to be a really cool challenge about this later. I don't know exactly where and when it's going to happen, but I believe there's a session after the break that will introduce all the challenges. So if you're interested in this, I really recommend you to look out for that. And with this, I think that is it.
OK. Thank you very much. So as you've seen, the QAOA circuits, they have these parameters. And these parameters very heavily influence the quality of the samples that you get when you execute the circuits on the hardware. Now, historically, in a lot of literature, the idea was to have a closed loop between the classical hardware and the quantum, where you optimize in this closed loop the parameters of the QAOA circuit. Now, one of the issues with that is that it leads to extremely long runtimes. And so what I'm going to present now is a package that we have in the Qiskit community, which makes available a set of different methods to find these QAOA parameters. So, right. As mentioned, the performance of the QAOA is extremely sensitive to these angles, beta and gamma. Right? If I choose them improperly, I might actually end up maximizing instead of minimizing, for instance. Finding these parameters is actually an NP-hard task. Right? There's papers that cover this. And you can also understand this quite intuitively. It is simply because we are navigating a very complicated landscape. You can see here the landscape for depth 1, QAOA, for an independent set problem with around 10 or so decision variables. And you can see that we already have many local optima in this optimization landscape, as well as regions where this is starting to be a little bit flatter. Right? So you can already see that if you put a solver into this landscape, it's going to have a little bit of a hard time navigating it. Right? Now, as already mentioned, executing this optimization also on quantum hardware is extremely costly, especially if you need to bring in some tools of error mitigations, right? There's also some things to consider, maybe when we look towards fault tolerance in the future, is that currently on noisy hardware, some gates, like the RZ gates with arbitrary angles theta, they're actually trivial to execute, right? They are phase changes of the subsequent pulses, and they have 0 duration. You can implement any angle that you want. When you start thinking of these algorithms in a fault-tolerant setting, this actually is no longer the case, and these RZ gates, which basically come for free, can become very costly, right? So this may be a little bit of a change of mindset that we'll also need when we start looking at these algorithms in a fault-tolerant setting. So there has been a lot of literature by the community in finding good angles for the QAOA. And there's a few different methods for this. I've got a few references on screen. This is by no means exhaustive. If you go and take a look at the literature, you will find many more papers on the topic. But one recurring concept is the following, is you leverage parameter transfer. Basically, we know that if you take, let's say, instances, problem instances, which are drawn from the same distribution of problems, then the QAOA parameters, they tend to actually cluster. So what this actually means is that I might be able to find QAOA parameters for a certain subset of problems, maybe at a fairly small size, and then transfer them to larger instances, right? So this concept here is what we would refer to as parameter transfer. Then there are many different strategies to find good initial points to start off the classical solver so that you're not starting close to maybe a barren plateau or maybe a bad point in the optimization landscape. And there's different methods for that. For instance, you've got this interp and Fourier, which were introduced by Zhu et al. In 2020. There's a lot of work that has been done on linear ramps, using those as starting points to optimize parameters. And these linear ramps can be understood as being inspired from annealing, which has some very nice connections in physics. And then you also have different methods, either based on these transition states in the landscape, where you train some parameters at depth p and use that to start the optimization at depth p+1, right? If you choose the extra parameters wisely, you will be guaranteed to go in a direction in the optimization landscape that improves the quality of the solutions. And then there's also a lot of work that has started to explore methods based off of machine learning. And then finally, for certain classes of problems, there are actually angles, good angles that are known. So for instance, you can show that if you train angles on tree graphs, these will have performances very similar for actual problems, right? Let's say if I take a tree graph with a regularity of 4, I can use those parameters for max cut on random 4 regular graphs, and I will get very good results by using those parameters. So the idea of the QAOA training pipeline is to make a lot of these methods available in the same place, right? So basically, if you're interested in training QAOA parameters, you can start playing around with this framework with a lot of the methods that I just showed in the previous slide. And what we have in this training pipeline is basically two classes in here. We've got the trainer, which is responsible for taking a cost operator, HC, and then outputting the QAOA angles for a given depth. And we have implementations for some of the works that were done in the literature, like these recursive transition states, the linear ramps, the interpolations, and optimizing in different bases, like for instance in the Fourier basis. And then some of these trainers, they also rely on evaluating the energy. Now we want to avoid hitting the quantum computer as much as possible to train these parameters. And so this is why we also provide tools to approximate the energy with, for instance, Pauli propagation, which has already been mentioned earlier today, or also matrix product state methods. And for some certain specific cases, you can actually get the energy exactly. Like for instance, with depth 1, there are methods to compute it efficiently classically. And if your problem is not too dense, maybe you can leverage light cones to simplify a bit the circuits that you need to evaluate. So with that, I'll hand it over to Elena to show some examples.
2 examples, to be concrete. There are actually a lot of really, really interesting problems in this repo, and it was difficult to choose. In the end, I'm going to be honest, I chose the shortest ones, so don't blame me for that. The first one is precisely what Daniel mentioned last. It's the idea that we can efficiently find parameters for depth 1 circuits classically in a really easy way. In this example, we have a graph that represents, with 100 nodes, that represents a cost operator for a max cut problem. I tried to print it out and gave up halfway through, but this is going to be as sparse probably up, if you remember. I also tried to print the circuit, and I also gave up, so there's just a combination of failures. But you can see at least that the circuit is quite long, even if it's depth 1. Now, in comparison to how large the graph and the circuit were, the code is actually quite short. You can see that all you need to do is import a trainer and an evaluator. In this case, we're going to pick the depth 1 scan trainer as well as the efficient depth 1 evaluator. You can check out more details on them in the documentation of the repo. And you instantiate your trainer, and you do trainer.train. This is going to give you a result, a dictionary with a lot of different fields. One of them is the optimized QAOA parameters. If we take a look at our optimization landscape, we will see that these parameters, by the way, are beta and gamma. We can see that we are actually able to really quickly pick an optimal, if not very, very close to the optimal solution. To give you an idea, running this took me about 15 to 20 seconds, whereas running a variational loop with this size of problem in a real quantum computer would take maybe, right now it would be about an hour. If you count queuing time and other hurdles, you can imagine it would take much, much longer. So this is just a really quick example of how you can leverage this repo. Another example is a bit more maybe convoluted or exciting, different. We're going to use recursive optimizers, and we're also going to be able to change the basis of our parameters. So in this case, the problem is much smaller. You can see it's another max cut problem, but our graph only has 6 nodes. However, we're going to give depth 10 to the circuit. So, you know, only, it was 6 qubits, but quite a long one. And here, I think that I did a better job at printing. Well, I didn't do anything, but the printing worked a bit better. In this case, we can see that we are performing a few different operations. One of them is getting the Fourier decomposition of the angles. We do this through the Fourier function. And then instead of optimizing the angles themselves, we use these Fourier angles. So we pick our trainer, we pick our evaluator, and then we apply the recursive optimization. And this is another cool feature of this repo, and it's that you can actually just plug trainers and evaluators one after the other. In this case, we're using a depth 1 scan trainer for the pre-trainer, and then a SciPy trainer for what we call the sub-trainer. And then we have a recursion trainer. Lots of trainers. And you will see that by doing this recursive optimization, we end up having, well, this is the Fourier decomposition of the angles, but we end up having, again, an optimal solution for our problem. Here, I forgot to put the red cross, but there's a tiny white dot there representing the solution. And you can also see on the second graph how doing this recursion actually helps us increase the energy. So again, a quick example. I'm sorry I didn't have time to go a bit more in detail into it, but if you're interested, I recommend you to check out. There's a tutorial about this in the repo. So, and if you have any questions, you can always reach out later. And I think that's it. Yes.
Okay. Thanks a lot. So we saw a little bit how to construct these high-level circuits that describe the algorithm that we want to run, how to find the parameters that go into them with the idea of doing the final sampling on the quantum hardware. But of course, before we run on the quantum hardware, we want to make sure that we create nicely optimized circuits to execute, right? So circuits that don't have too many gates, circuits that are not too deep either. So a lot of what Elena and I will now describe is also in a package on the Qiskit community, which we call the QOpt best practices, which refers a lot to best practices in constructing circuits for the IBM Quantum hardware. So let's take a look, right? The goal is to convert a high-level QAOA circuit into something that runs onto the hardware, right? This can mean the following. Let's say that I have a problem graph shown here, top right, and I need to map this into something like a heavy hex lattice, and very soon into a 2D grid, which will be given by Nighthawk, right? So this is very much a circuit routing problem with the additional, let's say, feature that we can exploit is that the cost operator has all the complexity in it, and fortunately for us, it's made of commuting 2-qubit gates, right? And because these gates commute with each other, we can actually leverage that in order to get shallower quantum circuits, and this is what I'll show you in the next few slides. Now, there's another degree of freedom that we can also exploit to get shallower circuits, which is the initial mapping, right? There is absolutely no constraint that I need to map decision variable number 0 into physical qubit number 0. I'm free to permute that around as long as I then respect the topology of the cost operator that will follow, right? And then I'll also touch on a few other hardware-centric optimizations that we can carry out. So let's take a look at routing circuits with commuting 2-qubit gates. And you can do this in different fashions, right? It can be optimal or suboptimal. Very, very naively, let's say I have a circuit with 4 qubits. Here, I'm showing a subcircuit of the larger graph. If I stagger these ZZ gates one after the other, I will have a circuit with a depth of 4. But if I conveniently place these in such a way that I execute as many gates as I can in parallel, I will reduce the depth from 4 to 2, right? And this means that by cleverly choosing the order in which we apply these CZ gates, and then later on also the layers of swaps that we will apply, we can actually get large reductions. And this is what is shown by the two last lines on the slide, is that if you take the standard Qiskit transpiler on optimization level 3 on some of the problems that you can see here, you will get a fairly large depth in terms of the number of 2-qubit gates, simply because we're not exploiting in there the commutativity of the gates. But if we use things like swap strategies, which I'll show next, you can get a 2-qubit depth, which is a lot shallower, right? Leading to better performance on hardware. So the idea is the following. What we want to do is we want to apply predetermined layers of swap gates and then greedily apply these RZZ gates as they come along. And if we do this also properly, we can leverage gate cancellations between a C0 or CZ gate of the RZZ and then one of the 2-qubit gates from the swap gate, right? So let's take a look at the simple example that I've shown here. We have 5 2-qubit gates that we need to route. I'm assuming that the topology of the processor in this example is a line of qubits, meaning that I can only do gates between neighboring qubits right here. So without playing around with the initial mapping, if I take this line of qubits, I can immediately apply a gate between Q0 and Q1, which would essentially be this gate here, which is that one. And the same here, I can apply directly this gate. And now I apply one layer of swap gates. This is predetermined, and this moves the qubits around and allows me to apply this next gate that comes up. And then I have the next layer of swap gates shown in here, gives me this fourth gate, and then finally we start repeating these layers of swaps and I get the last one, right? Now, what is known, for instance, is that if your problem is dense, fully connected, actually one of the optimal strategies to use is the one that I'm showing, and you can show that with a total of n minus 2 swap layers, where n is the number of decision variables, you can actually route a dense problem onto the hardware quite effectively and benefit also from a lot of these gate cancellations between the CZs. So it turns out that these swap networks are pretty effective. And what I want to show now here is how to exploit the degrees of freedom that we have in the initial mapping to further compress the circuit. So let's take a look at this random 3-regular graph. It's described by this network of CZ gates, or RZZ gates. And if I were to simply naively map decision variable 0 to qubit number 0, I would actually need a total of 8 swap layers to represent the full problem on the hardware. But it turns out that if you choose a clever permutation between your decision variables and your physical qubits, you can actually implement this full problem in only 2 swap layers, right? So this greatly reduces the depth of the circuit. And the way that we start to think about this problem is that it's nothing more than a subgraph isomorphism problem. So consider my chain of qubits here. I have 10 qubits placed in a line. This corresponds to the edges in black here of this coupling map. And then if I add one layer of swap gates, shown here in red, I get these extra edges here, shown in red. If I add another layer of swap gates, my coupling map is going to be enhanced by these gates in blue, right? And so now the question is, at which number of swap layers can I actually find an isomorphism between this graph so that it fits into this one? And this is the problem that we try and solve in this initial mapping step. So the problem is formulated in this way. Does there exist an initial mapping such that the cost operator can be implemented in L layers of a given swap strategy that can reach full connectivity? And this last condition here is pretty important, because if you can reach full connectivity, you are guaranteed that there is a solution to this problem that exists, right? So what I do is I have this swap strategy and I fix a certain number of layers that I take, right? I take the first L layers and I ask this question, right? So can I implement the problem? If the answer is no, then this simply means that the number of layers that I chose is too small, so I need to increase them. If the answer is yes, then, okay, maybe I've been a little bit inefficient. Perhaps I can reduce the number of swap layers and look for a different initial mapping that will allow me to represent the problem on the hardware. And so what we ended up doing is formulating this as a satisfiable problem, a SAT problem. And what's nice about the SAT problem, essentially, is that it has this easy, hard, easy pattern, right? So if I solve this SAT problem and the solution exists, I have an initial mapping that reduces the number of swap layers. Now I know that if I don't have enough swap layers, there's no such an initial mapping, right? So this is easy to determine here. If I don't have any swap layers, the coupling map is a line. I can very easily check whether or not I can embed my problem graph in that. If I have full connectivity, the problem is also easy to solve, right? And so what we then do is we do a binary search over this number of swap layers here to find the threshold here that minimizes the number of layers of swap gates in the circuit. And so this actually allows you to reduce by quite a lot the number of swap layers, right? And I think you'll show a couple of examples on that, won't you? Yeah, exactly. So stay tuned. And then finally, one thing that I also want to point out is that the hardware that we have also enables fractional gates. So these are gates where you can do any custom angle that you want. Now, the standard basis set of the hardware is the following, where you can see that all of the customizability, if you want, is in this RZ of theta gate. But it turns out that the hardware also has a mode of operation where you can do arbitrary X rotations and arbitrary ZZ of theta rotations. And this can be quite powerful for QAOA, because if I take a look at how RZZ is broken down into 2 CZ gates, it actually has a duration of 2 times the 2-qubit gate duration, right? But if I use fractional gates, then the duration of this is simply the duration of a single 2-qubit gate. So this actually allows us to get circuits that are less deep. A good example here is depth 3 QAOA on max cut on heavy hex. If I don't use fractional gates, the circuit lasts 4.6 microseconds, and the best cut that I report here was 20.5. If I use fractional RX gates only, this duration of the circuit reduces, right? So keep in mind that the metric that we are sort of comparing to is always the T1 time, right? So you want this to be as short as you can. So decreasing the circuit duration is a nice thing. And you can also see that this increases the quality of the cut that you sample from the device. And then finally, if I bring in the RZZ of theta gates, the circuit duration goes down to 3.7 microseconds. So I've shaved off almost about 20% of the circuit duration. And then this translates into better cuts that are sampled from the device. So with this, I'll hand over to Elena.
Thank you. OK. Last 2 code examples. If you were here, or if you were at QDC last year, you might remember the transpilation challenge with optimization, and this is going to sound very, very familiar. Maybe if you were not here, then I'm just going to show you now. I'm going to show both why we care about swap strategies and why we care about SAT mapping, and give you some numbers, which in some tables that I usually like adding to my slides. We're going to start off with the swap strategies. And for here, we pick an example cost layer. This is a 10-qubit QAOA ansatz, and I just cut out the cost layer part. If we naively decompose it, it will look like something, it would look like what we have here in the bottom. But let's see a little bit more what we can do. So in order to apply swap strategies, we need to import the swap strategy class from Qiskit. In this case, we're going to define a swap strategy from a line. And I forgot to delete the edge coloring part, but we are not going to define any custom edge coloring. If you want to know how that works, I recommend you to check out the repo and see what the effect of edge coloring can be. Now, we can see our sample swap strategy would permute qubit 0 and 1, 2, 3, 4, 5. Well, permute includes swaps between 6, 7, 8, 9, etc. So once we have our swap strategy defined, we can plug it into a transmitter pass that will be included in a pass manager. In this case, we are going to use the passes that are exposed in the QOpt best practices repo. These are the evolution of the passes from last year that were partially in Qiskit, partially in the QAOA best practices repo. In this case, we adapted them all to use this annotated ansatz, and they're all in QAOA best practices. This is just hints in case you were here last year and this rings a bell. We are defining 2 pass managers because I want to show you the effects of both of them independently. The first one contains 2 transpilation passes. One of them is called annotated prepare cost layer, and the second one contains the commuting to qubit gate router. Essentially what we do here is we collect blocks of commuting to qubit gates, and we route them using the swap strategy. On the second pass manager, we have 2 passes. One of them is called synthesize and simplify cost layer, where we essentially target the cost layer part of the circuit, and we make sure that we take advantage of these gate cancellations that I've tried. If you don't use this, the Qiskit pass manager doesn't find them as easily. Finally, we have this unroll boxes pass, which essentially removes the boxes from the circuit, giving you a standard Qiskit circuit that you can then plug into a standard pass manager or transpilation pipeline. So if we start off with our cost layer, the one I showed you 2 slides ago, and we run the first pass, we see that between our different RTZ gates, we get different layers of swaps. On the second figure, you can see how applying the synthesize and simplify cost layer just decomposes the different gates, and the unroll boxes removes the red box around them, meaning there is no more box. By applying these and incorporating them into a custom pass manager pipeline, we can get the best of both worlds. So what we do here is, if you're familiar with the Qiskit transpiler, there are different stages. The first one is supposed to be the init stage, but we just plug this before the init stage in a stage we call pre-init. So before starting to run the preset pass manager, we run all of these passes that I introduced before. We unroll the boxes, this means we remove the box, and then we run the pass manager. And this is maybe not the most optimized way. You can also try to play around with the different stages of the pass manager, but just doing this very naively and simply leads to, well, this is how the circuit looks like, but more importantly, leads to very nice results. So in terms of number of qubit gates, we're able to reduce from 261 to 230. The total depth gets almost halved, and the 2 qubit depth gets more than halved. So overall, this is like a quick trick that you can apply to your QAOA circuit. You can use these prepackaged tools from the repo, and then you can apply whatever you want with the pass manager, and you can get very, very nice results. Now, the second tool is the second technique is the SAT mapping. Here's another example. We have a graph. I don't remember how many nodes, 20 nodes, I think. We go through all of our process of the add-on, we get our sparse Pauli up, we have our cost operator, we build our QAOA ansatz. And I'm gonna show you a side-by-side example again of what happens if you just run the transpilation pipeline I showed you before with the pre-init and everything without SAT mapping, or with SAT mapping for the initial state. In order to apply SAT mapping, you can import the SAT mapper class from the QAOA best practices repo. You define a timeout because, as Daniel said, there's a chance that the algorithm will get stuck and you need to cut it early. And you simply call the remap graph with SAT, and this will return you the mapped cost operator, this mapped sparse Pauli up that you can then plug into your ansatz, and then you continue the pipeline as before. So this is, I think, visually quite easy to see that using the SAT mapping can be very handy. Of course, it depends on the problem you have, but in this case, we are able to, again, half the total depth and more than half the 2 qubit depth. So by combining the swap strategies and the SAT mapping, we can get some very nicely optimized circuits. With that, I think we're going to jump into the last section of our presentation, and we have 10 minutes.
Thank you very much. Oops. All right. So in this last section, it'll be a little bit shorter than the other ones, and hopefully it will give us a few minutes for questions as well. But we want to say a few words about how we actually execute all of this on the hardware, right? You've done a lot of effort to create circuits that look good, find parameters for them, and so on. So what do we do next? So with Qiskit, we have the sampler and estimator primitives. The sampler is typically the one that we end up using the most in optimization because it simply corresponds to run the circuit and get samples with that primitive. And these samples actually correspond to candidate solutions of the original optimization problem that we are interested in. Now, that doesn't mean that the estimator is useless. There are actually cases where you also want to estimate expectation values. This could, for instance, be if you need to train parameters, right? I mean, we don't necessarily advocate for that, but if you do want to train the parameters on the hardware, you would be using the estimator. But there are also versions of QAOA, like the recursive QAOA, that actually require us to compute the correlators between the decision variables. And these correlations are nothing more than expectation values, right? Now, when it comes to post-processing, this is often quite easy when it comes to combinatorial optimization because the bit string that the hardware has returned for me corresponds to the solution of the problem that I'm looking for, or at least a candidate solution, let's say. Now, as Stefan mentioned earlier, what you can actually do is use the CVAR aggregation method to actually arrive at, let's say, measures of how many more samples you need to take to compensate for the noise. And the CVAR technique is defined and discussed in the two references that I have here. So then what I want to do is I want to say a few words also about post-processing the samples classically. So this is definitely something that is valid and also encouraged to do. The core idea is that you draw samples from your quantum computer, and then you do some kind of classical post-processing on them to improve them. Right? And you can do this in a problem-informed fashion. The example that I'm giving here is for maximum independent set, where you can do some efficient, greedy classical post-processing of the samples, where, for instance, maybe I have the proposed solution here on the left, and you can immediately see that this is not a maximum independent set, because I have a node here in the middle that has edges with the other one. No. So you can see here that this node is creating two violations. So what this greedy post-processing does is that it computes the number of violations for the different nodes, and here you would see there's two violations, this edge and that one. This node has one violation, namely this edge, and this node has one violation. And then what this greedy scheme does is simply removes this node from the independent set, and you have a new proposed solution. Right? Now, one thing that I want to caution against when doing this is that the benchmarking is necessary to validate that you actually have value coming from the quantum samples and that not all of the performance is coming from the greedy post-processing of the samples, right? So whenever you start post-processing the samples classically, you need to ask yourself the question, is the quantum bringing some value as well? And of course, we hope so. Very well. With that, I'll quickly hand it over to Elena to say a few words about the functions again.
Okay, this is almost the last slide. We wanted to leave some time at the end for questions, and I also have like a big clock here saying that I have 7 minutes, which is adds a bit of pressure to the whole thing, but it's fine. I just wanted to give a shout out to the Qiskit optimization functions and explain a bit how we can incorporate them in the workflow that we've talked about up until now. So the tools that we've been introducing are tools. They are they represent different steps of the workflow. You can decide what to use. You can go to generic Qiskit. You can build your own. It's really up to you. But there are certain personas, there are certain users who don't really want to focus on choosing every tool for every single step of the way. And this is what Qiskit functions were created for. And in particular, as Stefan already mentioned, we have two optimization functions that fit in quite nicely into the workflow we've been introducing. These are the Kipu and the QControl ones. I won't go into detail with them because I think we have activations. How are they called? Well, we have the booths. You can go ask them. They're the ones who develop them. They're also going to be really cool challenges. I think they're probably some of the most fun challenges because you really need to beat like an objective. So again, I recommend you to stay after the break and see when these challenges are going to happen if you're interested. And we try to incorporate the use of the add-on into them so you can really see how the workflow fits together. And this is mostly it. Check them out, try them now. And with this, we can wrap up and summarize this talk, or the second part of the talk, where we talked about a lot of different tools, a lot of different techniques. We introduced 3 new or relatively new repos. One of them is the Qiskit add-on optimization mapper, optimization mapping add-on, this one. This has been recently published on PyPy, so you can just directly pip install it. The other 2 repos are part of the community. They are a bit more exploratory, and they are not directly pip installable from PyPy, so you do need to clone them. But in any case, I really recommend you to check them out. I really recommend you to try them out. And I would ask you to open issues if you find any problem, if you have any suggestion, any feature in the end. These are there to be able to support not only our research, but the community research. And we're really open to feedback and to proposals. So, try them out. Let us know what you think. Let us know if something is broken. We try our best, but sometimes things break. And I didn't read them, so the add-on, the QAOA training pipeline, and the QAOA best practices repo. And with that, I think we can finish. Ooh, yeah, this was another slide that said essentially the same thing. So we can finish, and let me know if you have any questions.